Thank you for coming to lecture 3 of the blockchain fundamental series. So today we're going to talk about cryptography concepts. But real quick, we're going to give a clarification on weekly quizzes and attendance. So to pass and get the certification, we said it before, but you can only miss at most 2 lectures, beginning with last lecture. So if you miss the first one, that's okay. And in terms of the quizzes that you take at the end of each lecture, overall you need like a score of 70% or above to get the certification, which is pretty standard. It's a C. So yeah, that's pretty much just to clarify for those who have been asking. And now Jesus and Mateo are going to talk about cryptography concepts. So yeah.
All right, so today we'll be talking about what is it that makes blockchain so secure. So how can we know for certain that the transactions that are going through blockchain are actually valid? So to motivate this, let's first talk about, and maybe this is like a coding lesson, but it's basically, let's imagine a system that requires trust, okay? Say you and your friends, it's just too complicated, like sending money back and forth like the whole month. And so you guys decide a system. You guys have a ledger, so kind of like a notebook or whatever. And anytime anyone like pays money for someone else, like, maybe it's like groceries, paying money for like, eating out or something like that. You guys, everyone lists their transactions on this ledger, right? That is public and anyone can see, right? And so at the end of the month, right? Alice owes $10, Bob owes $20, Charlie gets $20, and you get $20. Just by like doing basic accounting and adding all those numbers up, right? And so the protocol is as such, right? Anyone can add lines to the ledger, and at the end of the month, we just sort of settle up with real money, and people like either put money into the pot or get money out of the pot. But the problem is this is a terrible system because it requires trust. The problem is that like, with blockchain, you're transacting with random people that aren't just your friends, right? What if Bob just simply adds something like Alice pays Bob $100 on the bottom of the ledger, right? Theoretically, this is allowed because anyone can add a transaction on the bottom of the ledger, right? We need a system where the person who adds an item on the ledger is the person who pays, right? And in traditional finance, the solution we would use is like a bank. And a bank manages the ledger internally, and it verifies the identity of every single person who is adding to the ledger, right? The people who like add to the ledger, the only way to actually make an item on the ledger is by having the physical credit card or the details to their bank, right? So that's the way that the trust in the traditional finance system works. But the problem with this is that the system is centralized. You have the central authority that you just simply have to trust, and there's a lot of things like there's not a lot of transparency. You don't get to see this ledger; it's no longer public, right? And also, you don't know what they're doing with your money. Additionally, like this central authority could just go down at any moment, right? There's no way to make sure that the banks are actually financially sound. So how do we create a trustless system without a central authority? Well, the answer is with cryptography. And so I'll talk about digital signatures, and this is the first step towards building a trustless system. So intuitively, like maybe if you have this set up in real life with your friends, you just add a signature at the end, right? So whenever Alice needs to pay Bob, he just needs to write Alice at the bottom with her signature, and it should be, at least in theory, invisible for Alice to, or for Bob to forge Alice's signature, right? But the problem is that you might be thinking like, hey, in computers, anything can be copied, right? Say Alice's signature is just a JPEG or something. Like, can I just copy paste the JPEG along with the, Alice pays Bob $100 statement and just put it on the bottom of the ledger? But the answer is no. With the use of something called a public and a private key, okay? And we're just going to abbreviate this with PK and SK respectively. PK stands for public key. SK stands for secret key or private key. So everyone has their unique public and secret key. So Alice has a public key that's different than Bob's public key. Alice's secret key is different from Bob's secret key. And in fact, Alice's secret key is different from Alice's public key, right? Secret keys, just like the name, are meant to be secret. No one can see them except you. Public keys, however, anyone can see them, right? You just kind of publish it. It's just freely available for anyone to see. How does this work? Well, you have a secret key, right, along with a message, right? And the message could be like, Alice pays Bob $20, right? And you combine the message with the secret key to get a signature, okay? On the other hand, you can have a public key. So for example, you take Alice's public key, I'm Bob, for example, and I don't believe a transaction that went through that Alice quote unquote paid for, right? And so I'm going to take Alice's public key, which anyone can see, Alice's signature that was on the ledger, as well as Alice's message, like Alice pays Bob $20, right? And with 100% certainty, you can take all three things and then check if it's a valid or invalid signature, right? And there's a technical reason for why this exists, but we won't go into that for now. So basically, a signature in a computer is really going to look like a string of zeros and ones, okay? And so you can see that each one of these is a different string of zeros and ones, right? And in fact, these signatures are really solidly secure because if Alice adds another transaction, say Alice pays Charlie $15, right? You can notice that the signature changed because actually if you look at the diagram, the signature depends not only on the secret key, but also the message, right? So that means that if you change the message, you also change the signature, which means that if you want to save the signature of Alice pays $30, right, to Bob, right, you can't somehow figure out that this is the same signature that of Alice pays Bob $5,000, right? Like it's going to be a different signature. Now, can anyone see that there is a problem with this? There still exists a problem. Exactly, right? You said exactly right. So we know that okay, and then this is just an update to the protocol. The problem is that you could simply just take the valid signature, which we know is valid, and the statement, and just replicate the statement with the same signature, right? And it seems valid, right? Bob can't force Alice to pay $2,000, but they can just simply keep on repeating the same statement that was previously on the ledger, right? That was very astute observation. So the solution is just with transaction numbers. So basically, the message is not simply just Alice pays Bob $20 or something like that. We actually add a number at the very beginning. So 1, 2, 3, 4, and so on, right? And so if you were to replicate it, right, you need to add the number 5 at the beginning, right? Which means that the signature has changed, right? How do you find the signature? Well, you don't have the secret key, so you can't. And so that's a change of the protocol. Transaction numbers must be correct, and it also must be signed by the sender. However, there's still problems. What if Charlie racks up thousands of dollars in debt and just leaves, right? Well, the solution can be solved the problem can be solved just simply by having everyone pull in $100, for example, at the very beginning of the month, right? So Alice, Bob, Charlie, and you all pull in $100, right? And then basically what happens is that Charlie pays Alice, Charlie pays Bob, but as soon as Charlie decides to overspend, we just reject it. Everyone looks at the ledger and says, this is just not an invalid transaction. It's just as if someone tried to forge a signature. We just completely ignore it, right? And so that's the new protocol. Instead of settling up with real money at the end of the month, simply overspending is not allowed, right? And just a little note, just to tie things in, right? If you ever heard of blockchain, or sorry, like Bitcoin wallets or something like that, Bitcoin wallets are really just this: a public key and a private key. That's all a wallet really is. Basically, a number, which represents the public key and the secret key, which is why if you ever get a Bitcoin wallet hack, for example, that means that somehow they got access to your secret key. They're not supposed to get the access to that. And so, going going back to the current slides. Another thing is that this thing where you like add $100 to the system like magically, you might be like, how do people do that? Well, it's a step called mining, which you might have heard of, right? And Jesus will go into that very briefly.
So we're not done with this protocol just yet. There's still an issue with faking a payment. For example, Alice can broadcast, Alice pays Bob $20 and can just send it just to Bob. And everyone else will think Alice still has those $20. So how can Bob trust that Alice has broadcasted a message to everybody rather than just Bob? Well, we don't actually just listen to transactions. We do something called mining. So mining or proof of work is where we use SHA-256 hashes to sort of generate a proof that a certain amount of computational work was put into verifying the transaction. We create a method of verification. With SHA-256, anyone can verify that the creator of a block did a large amount of computational work, aka proof of work. So instead of listening for individual transactions, Bob can just listen for new blocks being mined or created or verified. And Bob should only trust the chain of blocks that have the most computational work involved. This is the basis for which blockchains are created on. Participants trust computational work, not a central authority. So let's go into hash functions. A hash function is a function that takes some input, let's say a message, a file, doesn't matter, it's just information, and it produces an output of fixed length. In this case, 256 bits was SHA-256. And that output appears completely random. But the hash is not actually random, it's entirely deterministic. Any one input that you feed into the SHA-256 function will produce the exact same output. However, it appears random and it's difficult to predict what the hash might be unless you first hash it. So here we see we put in hello, feed it into this black box we call SHA-256, and it feeds out 256 bits of output. And since it's 256 bits long, there are 2 to the 256 different possible hashes you can create. So computing the input from the output is just not computationally feasible. If I give you the hash of any hash, it's going to be pretty much impossible for you to find the input to that. The only way to find the input of a hash is to repeatedly try different inputs or different inputs until the hash matches. And that's called the hash collision. And up to this day, a single SHA-256 collision has not been found. Since the output appears completely random, the chance of obtaining the desired output is 1 and 2 to the n, or in this case, 256. Even if the input changes by 1 character, the output will completely change. So here we see hello and different permutations or modifications of it. It produces a completely different output. Here we see that again. So if I gave you the output over here, it's pretty much impossible to figure out what the original input is. And here we'll show you guys how that looks. So let's say if we edit this in any way, change the last one to 0, we just get a completely different output. Now, how big is this number, 2 to the 256? 1 and 2 to the 56 is incredibly small. It's, for comparison, the world population is 2 to the 33. The approximate grains of salt on Earth's beaches is 2 to the 72. Approximate stars in the observable universe is 2 to the 73. The approximate atoms in the solar system is 2 to the 186. And the approximate atoms in the universe is 2 to the 259. So only that's really larger than that number. So for proof of work now, let's say we make blocks or the ledger 50 transactions long. We then make it so that each transaction follows the protocol as Matteo described. A miner can just listen for transactions, make sure that the transactions are valid, include it in their block, And once they reach 50 transactions in their block, they then try to solve the block. And what that means is the miner is trying to find a certain number to add to the end of the block, such that the resulting hash of the entire block has a certain amount of zeros in the very front of it. So here we see that. That random number is over here. We'll get back to why we include the previous hash in the beginning. So we have the transactions in there. We have what we call the byte string or the nonce of the block. And we try to find this number such that the hash has a certain amount of zeros in the very beginning of it. And we have a little simulation for how this looks like. So here we see that a miner is just trying to randomly produce a random number to add to the end. And it's waiting, it's continually trying to do it until the hash results in a certain amount of zeros in the very front of it. And this generally takes a while. And once we find that certain number to add to the end of the block, it's very, very easy to verify that the proof of work is valid. We simply run the hash once and we see, oh, there's a certain amount of zeros in the front. We could say that block is valid. So if a miner finds that special number, so the hash of the entire block has a certain amount of zeros through it, that must mean only one thing, and that miner went through a bunch of computational work. So why does that miner go through that much work to do it in the first place? Well, when they're mining, before they find a number, they add a single transaction to the end where they give themselves, let's say 10 Bitcoin. And so that's kind of like the reward for finding a block. And one more thing, when we're creating the block, we include the hash of the previous block. And there's a good reason for this. So now when we edit a block, let's say 20 blocks ago, and we add another transaction, it changes the hash of that block, which changes the hash of the next block, which changes the hash of the next block, and so on. And what this does is, if someone modifies a transaction, let's say 10 years ago in the blockchain, the only way to do that is to recompute all of the future blocks, all of the other blocks, because now the new hashes won't have a certain amount of zeros in the very front of it. Now we have to compute the number again and again for each block coming forward. And here we see a fork. So let's say Alice did want to create a fictitious chain of blocks that differs from the network. What they would have to do is kind of race the original chain, because part of the protocol is that we trust the chain with the largest amount of computational work, and in this case, the most blocks to it. And the only way for Alice to beat the original chain is to have the majority of the computational power in the network. This is known as a 51% attack. So unless Alice holds 50+% of the computational power, they will never be able to keep up with the valid chain of blocks. Sure, they could probably get lucky, guess the 1 or 2 blocks, and which is why you shouldn't immediately trust a block that's mined. But if we wait a while, if Bob waits for, let's say, 6 blocks, it is very, very, very unlikely that those blocks were valid, basically, or those blocks were fictitiously mined. Oh, that's the end of the lecture.